In section 3.2, we're going to be looking at a specific application for linear differential equations, but this type of application is part of a much broader topic known as compartmental analysis. And compartmental analysis is a way to approach a problem that has multiple components to it, where we can compartmentalize the different parts of the application and identify inputs and outputs for each part. And we can simplify the solving process if we take this big complex problem and break it into these little compartments where the output from one compartment will serve as the input for the next. So it relates all of the pieces together, and it is a way to take a complex problem with multiple parts and organize it into a much more simple, approachable problem to work out. So I like these little compartment diagrams, and I'm going to use them quite a bit when I'm working these problems. The specific application we're going to be looking at in 3.2 is a mixing problem. So this little compartment also serves as like a vessel where we're going to be mixing fluids. And we're often going to have information about the input, and we're going to have information about the output. And we may also have some information about the initial conditions in the tank. And we're usually also told the volume of the tank. One of the examples that we're going to see in this section is a swimming pool. So this vessel kind of represents our swimming pool. It's got a specific volume of water, and at the start of our experiment or our analyses, we could say that there is a certain amount of chlorine dissolved in the swimming pool. And then we'll be given some information about fresh water coming into the pool. Maybe it'll be fresh water, maybe it'll be water that has a certain concentration of chlorine already in it. And then we'll also be given some information about water that's being removed from the pool, maybe through the filter or something like that. And what we're interested in is figuring out a function that will tell us how much of the solute we have in our system at any particular time t. So for the swimming pool example, our solute might be chlorine. I know in our homework examples, there are some problems with a brine solution. So it's like a brine is just a salt water, so it might be salt that we're mixing in. But we're interested in being able to track the amount of whatever that solute is in the system. And what makes this tricky is that we're constantly having new fluid added to the system, and we're constantly having fluid taken out of the system. And this is going to start as a differential equation, because when we know inputs and outputs, we know how the fluid in the tank will be changing, because we know the current conditions and we know what's being added to it. So we're going to be able to set up a differential equation that represents the change in solute over time. And the change in the solute is just the difference between the input and the output. What we'll typically know for these values is a rate and a concentration, and they're going to get multiplied together. And that will give us an input amount of our solute. And then for output, we'll have a rate and a concentration. And if we multiply them together, it will give us an amount of solute. What makes this a linear differential equation is the fact that our output concentration is going to depend on whatever the concentration is in the tank at any particular time, which we don't know. That's what we're trying to find a function for, to tell us the amount of solute in the tank at any particular time. So for the output concentration, we're actually going to be using variables. Concentration will be unknown, technically, but we will be able to set up a little formula for it that uses variables. Concentration is going to be measured as some sort of amount of solute compared to a volume of fluid that it's dissolved in. So that knowing that is going to be helpful for us to set up the piece that's going to have the variable in it, and it's how we're going to identify this as a linear differential equation. The generalities can sometimes get a little bit confusing. What I'd like to do is I would like to jump straight to an example so that you can see what type of information we're going to be given, how exactly we'll use that information, where we'll use that information. And really the only new part of this problem is going to be the setup of this new type of application problem. Once we get it set up, though, we're going to solve it using methods we've already learned back in Chapter 2 when we did linear differential equations. So it's really just the setup and understanding how these application problems work, and then from there it's gonna involve something we already know. So I've pulled this problem out of our book to take a look at together. It says a brine solution of salt flows at a constant rate of 6 liters per minute into a large tank that initially held 100 liters of brine solution, in which was dissolved 4/10 kilograms of salt. The solution inside the tank is kept well stirred and flows out of the tank at the same rate. If the concentration of salt in the brine entering the tank is 4/100 of a kilogram per liter, determine the mass of salt in the tank after T minutes. There's a second question they want us to address, but we don't need to worry about this to begin with. They also ask us, when will the concentration of salt in the tank reach 2/100 of a kilogram per liter? Don't worry about that part right now. What we're going to do is we're going to draw a picture to help us organize this data. This is our tank. We have a brine solution of salt that flows at a constant rate of 6 liters per minute into the tank. The tank's initial volume is 100 liters, and it says also initially 4/10 of a kilogram of salt is dissolved. So at the beginning of this problem, the amount, A stands for amount of salt at time 0 is 4/10 of a kilogram. The solution inside the tank is kept well stirred, and it flows out of the tank at the same rate. So it also flows out at 6 liters per minute. If the concentration of salt in the brine entering the tank is 4/100 of a kilogram per liter, so again, they're talking about the input here. That's the concentration of the input, 4/100 of a kilogram per liter. Determine the mass of salt in the tank at time t. What they're asking us to do is solve a differential equation so that your final answer is a function that gives you amount of salt in the tank. What we know is that the amount of salt in the tank is changing over time because new fluid is being introduced. That fluid that's being introduced has a different concentration than the fluid that's already in there. And the process of keeping this well stirred is going to constantly change the concentration. So the concentration coming out is going to be constantly changing. But we do need some sort of expression to represent the concentration of salt that comes out of the tank. And what we know is that it's going to be measured in kilograms per liter. A represents the number of kilograms of salt. So we're going to have A kilograms divided by the volume of the tank, which is 100 liters. This is an expression that we can set up to represent concentration of fluid in the tank at any time. If we know how much salt is in the tank, we can just divide it by 100 liters to get concentration. But we don't know the amount of salt in the tank, so we're going to leave it just as an A right now. A for amount. Another thing that we know about this particular type of problem is that the amount of salt changes over time based on the difference between the input and the output. So we've collected up all of our input and our output data. So when we create our differential equation, we're going to have dA dt equals input concentration is 6 liters per minute. Excuse me, input rate is 6 liters per minute. And input concentration is 0.04 kilograms per liter. And then for the output, the rate, again, they said was 6 liters per minute. And the concentration of the fluid leaving the tank, we can calculate using the formula A over 100. Because A is the amount of salt in the tank at any time. And to make it a concentration, we divide it by the volume of fluid that it is dissolved in. And we'll clean this up a little bit. I'll multiply where I can. dA dt, 6 times 0.04 is going to be 0.24. And notice that those liter units cancel because we have one in the top and one in the bottom. What we're left with for our input is 0.24 kilograms per minute. That's how the amount of salt changes over time that as it's coming in. We're gaining 24 hundredths of a kilogram every minute. But we're also losing some salt every minute because there's also an output. And if we multiply these together, we get 6A over 100. And because there's a variable in that expression, or in that term, we're going to take this entire term and I'm going to add it over to the other side of the equation. And we get dA dt plus 6A over 100 equals 0.24. I'm going to leave the units off. And I'm going to do one more simplifying step to hopefully make this look a little bit more recognizable. So 6 over 100 can be simplified to 3 over 50. And I'm going to just pull that A off to the side rather than writing it in the fraction. And now this format that we have right here is standard form for a linear differential equation. It might be hard to recognize because most of the linear equations we solved in the past were always dy dx. All we've done is we've changed our variables. We now have A as the output variable instead of y, and we now have t as the input variable instead of x. So we've got derivative plus some p function times the original function equals the q function. When we first learned this, we had this as dy dx plus p of x times y equals q of x. That is the standard form for a linear differential equation, and all we've done is we've changed the variables. Instead of y, we have a. Instead of x, we have t. When we solve linear differential equations, we use an integrating factor. We take our p function and we integrate it and stick it up in the exponent of an e. We're still going to do that. The only difference now is this is a function of t instead of a function of x. So we're just integrating a constant there. So we're just going to tack a variable onto it. And if you want, you could even change it to a decimal. So for linear equations, our integrating factor was what we could multiply by to make the left-hand side of this equation match up perfectly with a product rule. We said once we got really comfortable with this process, we could jump straight to the fact that once we find our mu, this is going to turn into a product rule between your output variable and your mu. That's what the left-hand side is going to turn into if we multiply through by the mu. And on the right-hand side, we would also have to multiply by mu as well. So to solve these linear differential equations, our next step is to integrate, because the integrate will cancel off the derivative there. That leaves us with a times e to the 3/50ths t. On the right-hand side, in order to integrate with respect to t, we're going to take the derivative of that exponent and it's going to get flipped in the front. So we've got 0.24 times 50 thirds e to the 3/50ths t plus c. We'll clean it up just a little bit. We can put those guys together, and we get 4 e to the 3/50ths t plus c. And then the last step to solve for a is going to be to divide over the e to the 3/50ths t that we have here on the left. And we want to divide each of the terms on the right. That'll make it cancel here, and it will make our general solution for the differential equations look like this. A of t is equal to 4 plus c e to the negative 3/50ths t. This is just a personal preference. All I did is I pulled that up to the numerator by making the exponent negative. Anytime I can avoid fractions, I try to do that. So it's, again, just personal preference. So this is our general solution. And there has been plenty of problems up to this point where this is all we needed to do, is find this general solution. We have an initial condition. So we can go past the general solution and we can find a particular solution by using that initial condition we were given. We were told at the start of this problem there were 4/10 of a kilogram of salt dissolved in the tank. So at time 0, there should be 4/10 of a kilogram of salt. We can use that information to plug into our general solution. This is a t value, and this is an a value, and it will allow us to solve for that arbitrary constant of c. So the a value is 0.4, and this is equal to 4 plus c times e to the negative 3/50ths times 0. Well, e to the 0 is just 1, and 1 times c is just c. So to solve for c, we're going to want to subtract the 4 over, and we get that c is negative 3.6. And with that information, we can now find, or we can now write the particular solution. Our particular solution is 4 plus c, but the c came out negative, so I'm going to say minus 3.6 e to the negative 3/50ths. This is the function that will tell us how much salt is in that tank at any particular time. And we're able to figure this out by just knowing that the change in the amount of salt over time is just going to be your input minus your output. So we've got enough information to set up a differential equation for the tank, and it turns out to be a linear differential equation. When we solve that, we get a function that tells us the amount of salt in the tank at any time. This was the first thing that we were asked to find in this problem. Determine the mass of salt in the tank after t minutes. Because it's a variable t, that means they know our answer is going to be a function. It's not going to be a number, it's going to be a function. So now let's look at the second part. It says, when will the concentration of salt in the tank reach 0.02 kilograms per liter? So a couple things I want you to notice first is how this question is asked. It's asked using the word when. When means we should be figuring out a time. We're trying to solve for time. Another thing you should notice is that it's asking us about concentration. And this function that we just solved for is not concentration. This function we just solved for is amount, absolute amount. But we have worked with concentrations during this application problem. Remember, concentration of our output, we had to set up as an expression. Concentration is amount divided by tank size. So we can use this function we found for amount of salt, and we can turn it into a concentration equation if we divide by the tank size. So concentration is equal to amount, and for us, that's been the A of t function, divided by volume, the size of our tank. So we can take our A of t function that we just found and we can divide it by 100 liters, and it will give us a concentration function. So 4 minus 3.6 e to the negative 3/50th t, all divided by 100, and now we've got a concentration formula. We're trying to solve for the t when concentration is 0.02. So we're plugging that concentration in for the c and solving for the t. So just one step at a time, I'm slowly going to do opposite operations to get this t all by itself. So I'm going to start by multiplying both sides by 100. That'll cancel off the divide by 100, and that's going to give us 2 is equal to 4 minus 3.6 e to the negative 3/50th t. Next, I'll subtract that 4 over, and when I do that, I get negative 2 is equal to negative 3.6 e to the negative 3/50th t. Then I'll divide by that negative 3.6, and this comes out to be a repeating decimal, so I'm just going to put the exact equivalent, which is 5/9, is equal to our e. So now we're at the dilemma where we need to get that t out of the exponents. We can't really do anything further because it's up in the e. So our next step is to take the natural log of both sides. So we want the natural log of 5/9, and I am good. This again is just some crazy decimal, but I will have to write it down. I got negative 0.5878, and all they're going to do is the ln and the e will cancel, and it will leave us with our coefficient, or our exponent, of negative 3/50th t. So our very last step to solve for t is to divide by the negative 3/50th. And I get about 9.8 minutes. It will take approximately 9.8 minutes for the concentration in that tank of brine solution to reach 0.02 of a kilogram per liter.